Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover the basics of a metric space. So the question is, what is a metric space? Well, this is a set X which has a defined metric. And what that means is for all x, y, and z in this set X, these four properties hold, which means they're a metric, which is kind of like, it's a measure, it's a distance. That's why I call these things d here. So what it says is the distance between x and y is always going to be bigger than 0. So when you're thinking about distance, this is the distance between, say, here and here is always going to be a positive number. Say if that distance is equal to 0, if the distance between x and y is equal to 0, that must mean x is equal to y. So really, another way of writing that is the distance between x and itself has to be equal to 0. So, the distance between here and here is going to be 0. The distance between x and y has to be the same as the distance between y and x, since distances are always positive. So these two distances are the same regardless of what direction you're going. Think about driving to work. The distance from your house to your work is the same distance as your work to your house. And then finally, the triangle inequality holds. And that means the distance between x and y plus the distance between y and z has to be greater than or equal to the distance between x and z. And let me kind of explain that triangle inequality really with a triangle here. So let's say I have this triangle. And what I'm going to call this is I'm going to call this, this will be, say, x, this will be y, this will be z. So what we're saying is that this distance right here, this here is going to be the distance between x and y. This distance here is going to be the distance between y and z. And I can see that this distance plus this distance is clearly bigger than the distance between, these 2 points, which is going to be x and z. Now I drew a right triangle, but it doesn't really matter. So, even if you have something like this, you can still see the distance between the legs is always going to be longer than the hypotenuse is really what we're trying to say here. So that's why they call that the triangle inequality. So I'm just going to kind of verify this with, let's talk about, the Euclidean space just in one dimension, and then we'll break it into 2 dimensions, and that'd be a good spot to stop. It'd be a very basic introduction of metrics in a well-known set. So let's start out with just the real number line. Let's say just R1. So what I'm going to say is, R1 is what we call this, or R is just going to be, let's say a horizontal axis, so the direction doesn't really matter. And, we have like 0 and 1, 2, and 3. Now I'm talking about all real numbers, so, all the numbers between as well. So this is going to be my set X. So X is going to be the real numbers. And I have to define a metric on this set. So that means the distance between any 2 points on this set, say x and y, is going to be equal to the absolute value of x minus y. And it makes sense because if I asked you guys informally, let's say, what's the distance between, let's keep these things positive so it's a little more obvious. What's the distance between 4 and 1? Well, if I wanted the distance between the 2 numbers, say 4 and 1, and I don't have to choose integers, or whole numbers, I'm just doing it to make the math easy. This is going to be the absolute value of, well, I guess it depends on what you want to call x. Well, let's call this thing x, let's call this thing y. So this is, x is going to be 1, and y is going to be equal to 4. And we can see that this is going to be the absolute value of -3, which is equal to +3. So, and we could tell that distance here, I had to go 1, 2, 3 to get there. So that's why that distance is equal to 3. Now, we can verify some basic things when it comes to like this metric, and then we can kind of talk about in the general first. Okay, so let's extend this thing out a little bit farther. Let's just take a couple extra numbers, and I'm going to do some numbers in the specifics, so then we can move into the general. So, for instance, does this make sense? Number 1, does the distance between x and y, is it always positive as long as the numbers are not the same? So in this case, I could say I was finding the distance between 4 and 1. So what I had is, as long as the numbers are not the same, then there's going to be some defined difference that's not going to be equal to 0. And it could be a positive number, it could be a negative number, but we don't care because the absolute value of any number is always going to be that positive number. So we can see that the distance between two numbers that are not the same in this case is clearly bigger than 0. This is greater than 0, so really property 1 holds. So that's good for at least the numbers 1 and 4. Now let's check this. What about the distance between, I don't know, let's say 1 and 1, 1 and 1. Well, this is going to be the absolute value of 1 minus 1, which is going to be the absolute value of 0, which is equal to 0. So we can see that the distance between two numbers that are the same, the distance between x and x is equal to 0. And the only way you're going to get 0 is if these two things are the same. So really I'm trying to say that it works both ways. So this if and only if means if this is equal to 0, then the two elements are the same. If the two elements are the same, then their distance is equal to 0. That's what that if and only if means. Next, let's double check. It says the distance between x and y better be the same as the distance between y and x. So I've already found the distance between 4 and 1. Let's find the distance between 1 and 4 and see if we get the exact same number 3. So this is going to be the absolute value of, this is going to be, did I write that wrong? Let's see, this is x. No, I actually called this x. Okay, so in this case, I'm going to call, I'm going to say this is going to be 4 minus 1 because I'm really trying to verify that if I change the orders here. So if I call this thing x and this thing y instead, it shouldn't matter. So the distance between 4 and 1, so this is the absolute value of 3, which is going to be equal to 3. So I get the same thing both times, regardless of the order that I take its distance from. And then lastly, I need the triangle inequality, which basically means I need 3 points. And I've written that 6 here just because, might as well have another point here. So now we have 1, 4, and 6. And I have to kind of verify that the distance between 1 and 4 plus the distance between 4 and 6 is always going to be greater than or equal to the distance between, than 1 and 6. So I'm basically taking, the distance here plus the distance here better be greater or equal to the distance from, the beginning to the end. So this is going to be the distance between 1 and 6. So this distance here we know we've already calculated. This is equal to 3. Now this distance between 4 and 6 is going to be the absolute value of the difference being, a 2 or negative 2 depending on what direction you want to go. So this is clearly going to be equal to 2. And if I find the distance between 1 and 6, we know that this is going to be equal to 5. So this inequality holds because it says it has to be greater than or equal. In this case, it's equal to 5, so we are good. So far, boom, 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 boom. All 4 properties are held for at least this specific case. So, and you can kind of see how this works for the general case as well. And I guess proven is kind of like beyond the scope of this discussion, but really to kind of explain, how this is a metric on this real number line. So, what if I want to move into R2? And we'll just continue with the specific as opposed to the general because this is just an introduction of. So let's say x values now, all our x values are going to be ordered pairs, so this is going to be, an R2. So what I'm talking about is, I'll draw it down here, it's going to be this side here. So we're talking about ordered pairs. And we can be really specific with a couple points. Let's say our points are, 2, 1. Let's go 4, do you want to make it that messy? I do not. So let's say 4, 1, and then let's go to 4, 2. Let's do these points here, and this will be relatively simple because I really want to talk about like our first point. Let's say, so I'm going to say point 1 is going to be the point, say 2, 1. Point 2 in this case is going to be the point 4, 1, and then point 3 is going to be the case 4, 2. And I want to use these points just to kind of verify that these properties work. So first, let's start out with a metric. So I'm going to say the distance between point P and point Q is going to be equal to the square root of, well, if P is equal to, say, x1, y1, and then q is equal to, say, x2, y2, then our distance formula is going to be equal to the difference between the x's squared plus the difference between the y's squared. What's really kind of interesting is we just did this in one dimension, and this is just the expansion of that same formula in 2 dimensions. So when I said back a whole 5 minutes ago, when I said the distance between these two numbers is simply the absolute value of the subtraction, well, if you look at this, that absolute value really comes from that formula there, that if you're only one dimensional, you're going to only have one component piece here. So then, you know, this will simplify to this. But now since I'm 2 dimensional, I'm going to have this for, this axis, and then I'm going to have to add another one of these for this vertical axis. And then you can see that it can extend to 3 dimensions by pulling here. And we've talked about this before a little bit as well. So this is just extending this exact idea into 2 dimensions as opposed to what we do in 1 dimension. So let's just kind of verify that this still works. Okay. So this will have more interesting triangles than, say, the last one that went from 1 to 4 and then 4 to 6. Okay, so I'm going to find, just kind of verifying that this works for, say, property 1, property 2, property 3, property 4, and that's just going to be, say, for these 3 points here. So very specific stuff. So let's see if it works for number 1. And then we can kind of see that it would work in the general as well. So what about the distance between, say P1 and P2? So 0.1 and 0.2. Well, this is going to be equal to the square root of, well, I'm going to subtract the x component. So this is going to be, it's x2 minus x1. So x2 minus x1. So 4 minus 2 squared plus. Now I have to subtract the y components. So this is going to be 1 minus 1 squared. So we can see that this is going to, that goes away because that'll be 0 squared. So this is going to be 4 minus 2, which is 2 squared, which is 4. So this would be the square root of 4, which is in this case is going to be equal to 2. And we can see that was kind of clear, like the distance between these 2 points is 2 units. Can you also tell that this will always be positive? The reason why is I am summing squares here. So, no matter the number here, that this is going to be, well, the smallest it can be is 0, and that's going to be kind of our next property to prove that they'll be equal to 0 as long as the points are the same. So, this, assuming that the points are not the same, this will always be, bigger than 0. Or at least one of these things will be bigger than 0. And then the square root of a positive number will be a positive number. So it really does work in the general in that case. Let's verify that the distance between P1 and P1 is also equal to 0 itself. So this would be the square root of, now remember, I'm just choosing this point twice. So if I kind of write another 2, 1 down here, now it's going to be x2 minus x1, so 2 minus 2, squared, plus y2 minus y1, which is going to be 1 minus 1 squared. So in this case, I get 0 squared plus 0 squared, so this would be the square root of 0 squared plus 0 squared, which is the square root of still 0, which is equal to 0. So we can see that this property holds that the distance between a point itself is going to be equal to 0. Or if this distance is equal to 0, the only way for this to happen is these two things have to match, here and here, which means that the points have to be the same. So really, if this is true, then this is true. If this is true, then this is true.